Up here. So the first shortcut we're going to see, again, this for the shortcut to work, we're going to need to start off with I equals 1. So it's the sum of I equals n of the first I equals 1 to n. And this is not universal. Some places will say j, some places will say k. But the main thing is that you get this 1 right here, and then the summation, if you're summing all those up, you end up with n times c to solve out whatever it is. So if I give you this problem right here, I say, all right, we've got I equals 1 to 7 of 4. Well, that's going to be 4 times 7 because you're adding 4 together 7 times, and you get 28 as the solution here. Did y'all do any of this during Algebra 3 last year? Okay. All right, the next thing I want us to look at is when this term is not a constant. So let's say that I ask you to come up with the sum of the first 1,000 numbers. Okay. Well, again, we don't want to say 1 plus 2 is 3, 1 plus 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4. We don't want to do that, right? We don't want to sit there, even if we have a calculator, we don't want to sit there and even type all those numbers into the calculator. So what do we do here? Well, let's say we start off with I equals 1 to 1,000 of, now this is going to be of I. And I is not a constant. I is changing throughout. So what does this look like as a sum? Well, it looks like as a sum, you've got 1 plus 2 plus 3 plus, and then we're going to have somewhere out here 998 plus 999 plus 1,000, right? And that's what we're looking at adding together. Now, let's just say that we're given that as a situation. And you're asked, okay, let's solve this out. Let's see what it is. Well, again, I mentioned we don't want to sit here and physically add all those numbers together. But I intentionally wrote it out like this because there is a pattern that is going to exist right here. And that pattern is let's take the first number and the last number. Okay, the first number and the last number, what do I get when I add those together? 1,001, right? And let's take the second number and add it to the second to last number. What do we get as our sum here? 1,001, right? And let's take our third and add it to the third to last number. What do we get when we add those together? 1,001. Do we see a pattern that's happening here? Good. Woo, I was afraid I wouldn't. So, what is it that we're really doing here to come up with this sum of all these numbers? We don't need a bunch. We need to know more than a bunch because we can't say a bunch times something.
So number of terms plus 1. What was that?
Keep going with it. You're on the right track. Huh? It's 500, right? If you've got 1,000 terms, and each time we're taking out 2, so there are 500 of them. So to get this sum, we would actually say 500 times 1,001 to come up with the answer. So that would be 0.05005. So we would come up with 500,500 as our solution here. Now, how is that as a shortcut? As a shortcut, that can be thought of as n times n plus 1 over 2. Now let's think about how, for the purposes of this problem, we could think about n over 2. N represents what? Number of terms that we're dealing with. What did n plus 1 represent?
Oh, well, I guess in this scenario,
The sum, right? The actual sum of doing that. So here's the sum, and then we're going to multiply it by the number of terms, and the number of terms is 1,000 divided by 2, which is the 500 there. So that's how we come up with, if we have I equals 1 to n of I, the actual summation is n times n plus 1 over 2. Now, the others that I'm going to show you can be proven, or proved, I guess, by induction, which is what we did last year. If you want to look at proofs by induction again, you can. But it starts off with, if we have I equals 1 to n of I squared. Well, let's look at what that looks like as far as a sum is concerned. Well, we could start off with 1 plus 4 plus 9, right? And then somewhere out here we get an n squared there. We want to look at what the sum of that is. The sum of this is represented by n times n plus 1 times 2n plus 1 all over 6. So finally, if I want to look at an example of that, then I can say, okay, what is the sum of the first 7 terms from, let's say we have 7 plus 28 plus 63 . And then out here we have 700. Well, what is this? How do we come up with 7? How do we come up with 28? How do we come up with 63 here? Okay, so this will be 7 times 1 squared, 7 times 2 squared, 7 times 3 squared. What would this last term be? 7 times 10 squared. Is everybody okay with that? Okay. So we could say this is I equals 1 to n of 7i squared. Now, with summations, an easy thing you can do in summations is you can actually take this constant out front. It makes it easier. So it's 7 times I equals 1 to 10 of just I squared. So at that point, it's going to be 7 times. All right? So n is 10. What is n plus 1? 11. And what is 2n plus 1? 21. All over 6, right? Well, let's simplify. This 6 would become 2, and this 21 would become 7, and then that would make that become 5. So we've got 7 and 7 is 49 times 55. So we get the sum of these terms to be 2695. So if I add 7 plus 28 plus 63 plus whatever 7 times 16 is, and 7 times 25, and then 7 times, keep going till you get to 7 times 10 squared. You add all those numbers together, you get 2695. All right, the last one, I'm not gonna do an example with it, is I equals 1 to n. This one very rarely shows up for the purposes of what we're doing here, but it's I cubed. The formula, I wouldn't even teach it to you except for the fact that the formula's pretty easy. Is what you would do with I, but squared.